Welcome to the fourth week of the machine learning module. This week we will discuss classification. In the first two parts of the lecture, we will discuss linear classification. We will cover perceptron and logistic regression and multinomial logistic regression. We will also discuss how to evaluate classification performance. In the third and fourth parts of the lecture, we will introduce support vector classifiers, and we will introduce linear classification, nonlinear classification, and also kernel trick. So let's start with the first part. The application that we will use to demonstrate classification concepts is diagnosis of heart failure. Heart failure is the primary cause of heart disease, and it happens when the heart is too weak or stiff and therefore unable to pump blood sufficiently. Diagnosis of heart failure is best done using imaging, either MRI or ultrasound. And the two markers that we can calculate from the imaging is ejection fraction, which is the proportion of blood of the left ventricle pumped out with each contraction, and global longitudinal strain, which is the percentage of change in length of the heart during cardiac cycle. So the machine learning task is to predict heart failure from the measurements of ejection fraction and global longitudinal strain. And our data set is plotted here. Each data point represents a patient. Patients with heart failure are plotted with red diamonds, and patients that are healthy are plotted with blue circles. We have two labels: on x-axis ejection fraction, on y-axis global longitudinal strain. And the healthy patients are given label 0, and patients with heart failure label 1. We already seen that we can fit a linear classifier to this problem, which results in linear decision boundary with this kind of equation. This is the boundary. And we achieve accuracy 0.96 on the whole set and 0.92 with cross-validation, which is quite good. Now, let's have a closer look at linear binary classification. So firstly, we need a linear decision function to construct a linear binary classifier. So binary classification means simply that we have two labels, and linear means that we have linear decision function. And this function is in a form of a multivariate linear function. So we have a number of parameters that correspond to the number of features, +1. That's the same as we had for regression. And then the decision boundary is where this decision function is 0. So we can see here the decision function plotted in blue, it's a plane, and the boundary is where it's 0, so it's a line. And we predict the labels based on the sign of the decision function. So when the decision function is positive or equal to 0, we will predict label 1. And if the decision function is negative, we will predict label 0. So how do we find the decision function for our particular problem? There are several algorithms we could use, and we already know one of them, which is perceptron. So to fit perceptron model, we minimize perceptron criterion. And this criterion penalizes misclassified samples proportionally to their distance from the decision boundary. This distance is expressed through the absolute value of the decision function. So you can imagine that when the absolute value of the decision function is large, the sample is far from the boundary. If it's small, it's close to the boundary. So this will be our penalty, and we only penalize samples that are misclassified. So perceptron model can be fitted through perceptron learning algorithm. First, we pick a random sample, and then we check whether it's misclassified. And if it's misclassified, we will amend the parameter vector. using one of these equations depending on the label. If it's correctly classified, we do nothing. And we will iterate between these steps until convergence. This parameter eta is the learning rate and is usually set to 1. So this classifier works in practice, but it has some disadvantages. First of all, it does not always have a unique solution. And secondly, convergence is not always guaranteed. There is another problem that we can encounter in classification problems. Sometimes it's difficult to decide what the correct class should be, in particular if the samples overlap, as you can see here. So for this reason, it's useful not to only predict the label, but also to predict our confidence about the label. And we can do that using probability. So logistic regression is a model that can help us to predict also confidence using probability about our predictions. And it does that by converting the output of the decision function to a probability using sigmoid function. So you see the equation for the sigmoid function here. Here is the plot. On a x-axis, we have the output of the decision function, and on y-axis is the sigmoid. And you see that the range of the values of decision function is squashed to the range 0, 1, which can then be interpreted as probability. So probability of label 1 given feature x will be assigned this output of the sigmoid function after it's been applied to the decision function. And because the probabilities have to add up to 1, the probability of label 0 given feature x will be assigned 1 minus sigmoid of decision function. Here is the plot. So red line, red solid line shows the probabilities for label 1, and the dotted blue line shows probabilities for class 0. Where they cross, we get the decision boundary, and we see that happens at probability 0.5. A logistic regression model can be fitted using cross-entropy loss. In this loss, we have the labels, and we also have a logarithm of the probabilities pi, which will denote the probabilities for the class 1. So to understand this loss function, let's see what happened for an individual sample. So let's say that the sample has label 1. We can then calculate the penalty for this sample by setting yi to 1, and we'll get minus logarithm of pi. Pi is the probability for class 1. And we see from this plot that when probability is 1, we get 0 penalty. And if probability is close to 0, we get large penalty. If we take a sample with label 0, we will get a penalty minus logarithm of 1 minus probability. And this creates the opposite situation. So when the probability is 0, we'll get 0 penalty. And when the probability is close to 1, we get large penalty. So we can see that cross-entropy loss, when it's minimized, ensures that the probabilities pi, which are the probabilities for class 1, are similar to labels yi. This minimization is performed using numerical methods such as gradient descent, and in this case the convergence is guaranteed because cross-entropy is a convex function, so this is lots of good properties for logistic regression. Logistic regression is implemented in scikit-learn in object logistic regression. We can feed the model and predict probabilities as we are used to already. But what we can also do, we can evaluate the decision function and the probabilistic prediction using predict proba. Here we see the result of applying logistic regression to our problem. We obtain slightly different boundary than with perceptron, and we have cross-validated accuracy of 0.94, which is better. So we already seen how to plot the results of 2D classification by plotting the decision boundary. But there is another option that we have. We can sample the whole two-dimensional feature space. So we will create a grid that covers all this region, two-dimensional grid. And then we can predict the labels for this feature space. And once they are shaped to the right format to create an image, we can plot it using matplotlib function contour F. So we used color map summer here, and this color map gives us yellow color for high values and green color for low values. So green color for us will be label 0 and yellow color label 1. So the only tricky bit about this code is that we always have to ensure that we have the correct shape for either plotting or prediction. So that's why we have relatively a lot lines of code to do that. We can similarly plot probabilities as well. We'll predict them on the feature space using predict proba. And this function will return probabilities for all the classes. So we will select class 1 in this case and reshape it to the image. And then we can plot using contour F as before. So we can see this is a very similar plot, except that we have a smooth transition, which expresses the confidence around the decision boundary. We can also plot the isolines of this function using matplotlib function contour, and we can also label the isolines using C-label. So here we show how probabilistic predictions can improve our understanding of the predictions, because it gives us, they gave us a numerical evaluation of confidence. So we have two samples, both of them have predicted label 1, but they have very different confidence. In this case, on the left, the sample lies in the region where there is lots of patients with heart failure and no healthy patients. So it's very clear sample with that should be labeled 1, and that's reflected in confidence 0.99. And in this case, we have a sample that is surrounded by both classes. So we are probably close to decision boundary, and the confidence is 0.55, which is low. So we can see, even though both of these patients might have heart failure, the confidence is very different. So that's the end of the theoretical part for this part of the lecture. Now it's time for an exercise, and we will do a practical exercise using a Jupyter notebook, univariate logistic regression. So please download this notebook now and do the exercise. You can watch the solution that is available as a video on Kids. And once you are done with the exercise, please watch the second part where we will discuss multi-label classification and performance of classifiers.